Welcome to episode 12 of the UTX podcast and the second episode of our three-part machine intelligence series. Discover deep learning and the future of artificial intelligence with us today. The interdisciplinary field derives its beauty from its comparatively advanced maturity despite its mathematical complexity. Applications of computer vision, computational linguistics, and generative models have already achieved widespread adoption and have both been used in commercial applications, but also in popular culture.
In this UTX episode, we present an in-depth look inside the intuition, the major application areas, as well as the challenges of deep learning. The deep learning industry is expected to grow tenfold to over 40 billion US dollars in the next handful of years. In the next episode, we will cap off the machine intelligence series with a trifecta of high potential hardware, software, and networking concepts before hopping on to further topics.
Welcome to the UTX podcast, where we present you a utopia created by technology, presented by your Techniax. I am Valentin.
And I'm Ani, and today we're going to talk about deep learning. As usual, we will introduce you to the concepts of deep learning and then present the most important types of deep learning algorithms to date. We will also cover the applications and challenges of deep learning and then conclude with our signature Utopian day in the life. A small heads up, this episode will presume that you have some knowledge of machine learning. We recommend that you click pause, check out our last episode on the future of machine learning, and then come back and continue. We'll wait for you, promise. Okay, you're back. Let's dive into it.
So what is deep learning? And deep learning is a type of machine learning based on artificial neural networks. Those artificial neural networks are deep because they have several hidden layers. Hidden layers are all the layers between the input and the output layers. So additional mathematical complexity essentially is introduced into a deep learning algorithm. A deep learning algorithm learns patterns and representations in unstructured data and is able to solve all ranges of tasks that machine learning, or in the universe of machine learning, which is classification, regression, and clustering. We will cover its areas of application in a later section, more detailed.
And now, just shortly to present the difference between machine learning and deep learning. And there are a few, but we'll just go over the most important ones. And primarily, the difference is in the capabilities as well as the approach. So while machine learning is used for simple and bit complex problems, deep learning is suitable for more complex problems. Another difference is the approach to problem solving. A machine learning algorithm breaks down a problem into subparts, solves each part, and then produces the final result. A deep learning algorithm, on the other hand, takes the input for a given problem and produces the end result using a so-called end-to-end approach.
Before we go into neural networks, and you will also find this in the first machine intelligence episode or the 11th episode of our podcast series about the future of machine learning, we need to still highlight an important distinction in the field of machine learning, which is between supervised and unsupervised learning, because you find that distinction also in deep learning. In supervised learning, training data is labeled. So the algorithm has some existing input and result relation to work with. So it can learn which sort of input creates which sort of result, and the result is being determined. In unsupervised learning, the training data is not labeled, so you count on the algorithm to not just find the hidden relations between input and output, or between input and result, but also determine what the result actually is. An example here is clustering, which most of the times is unsupervised, where you ask the algorithm to determine both the clusters or the groups, as well as to which cluster any particular data point belongs to. An example of supervised learning would be an email spam filter, where you give the algorithm a large data set consisting of emails which were already labeled as spam or not spam. So the algorithm learns what the characteristics are, what the features are that determine which email, what the set of features is that determine which email is spam and which is not. So it can apply that, it can generalize that onto newly incoming emails and figure out if those are spam or not. To learn more about machine learning, as already mentioned, check out our previous episode.
Now, the special thing about artificial neural networks are that they are learning algorithms that resemble the way that many biological organisms learn in practice. So they can learn an arbitrarily complex mathematical function to solve a computational task. And this is done in a process called feed-forward propagation. The artificial neural network transforms input vectors or matrices that represent these numerical representations of several features into a prediction. And it does so based on mathematical operations carried out over several steps.
And these steps are being executed in layers. A artificial neural network consists of an input layer, an output layer, and at least at least two hidden layers between them. Sorry, at least one hidden layer, but if it's deep, then at least two. So the input layer consists of several nodes or neurons, each representing one input feature. At each hidden layer of the network, the input is multiplied by a weight, added, or a bias is added, and the input is then fed into a nonlinear activation function, which has the useful property to output results between 0 and 1. If you would just stack linear functions on top of each other, you would just get a giant linear function, which wouldn't increase the generalization and the predictive power of the algorithm. So you use nonlinear activation function. Each hidden layer contains several nodes, with each node representing a different weight as a multiplication factor to the weighted sum of inputs derived from the previous layer's nodes activation function outputs. If that sounds complicated, well, it is.
And this final prediction is then compared to the expected result in what is known as a loss or cost function. Now, for the process of optimizing predictions, you want to minimize the cost functions, or in other words, make the expected or the final prediction very close to the expected results. And this, to do this, a so-called gradient descent is used. And you could sort of visually imagine this as descending a point estimate down a U-shaped loss function to find the value or the lowest point of this U-shaped function.
And what's amazing about the neural network and what allows it to learn is because you can update the weights. And the way that this is being done is in a process called backpropagation. What serves as the input and as guidance is the output of the loss function. It serves to update each of the network's nodes, each of the weights of those nodes, and it uses partial derivatives and chain rules of nested functions as mathematical properties or as mathematical tools, let's say, to perform this backpropagation process.
Now, deep learning does sound very complicated, but I think the most complex part is over. Now we get into the most important deep learning algorithms to date, and we'll take a bit of a deep dive into how they work and also a bit into where they can be used.
No pun intended.
So we begin with one of the most widely used methods, which is a convolutional neural network that we will abbreviate to CNN now. And these networks are capable of detecting patterns and objects in images and videos. So the challenge that that CNNs are able to solve is that the input data, especially if you have images and videos, are often quite complex, and any learning results are very hard to generalize. And one thing that you have to note here is that if an algorithm is overfitted to a training set of data, which means that it is the weights and biases are adjusted almost entirely to the training set data, it will not be able to generalize its pattern prediction strength to apply it successfully to data beyond the training set. So it'll have a very high internal validity, meaning it'll work well with the training set, but it will have a very low external validity, meaning that you can use it beyond the training set. Now, to account for this, CNNs use a process called regularization. And this basically incentivizes the algorithm to reduce mathematical complexity by simply penalizing it for it. And in the CNN specifically, is achieved by altering the way that the hidden layers work. Now, for a CNN, if we take this example, images and videos are basically just a bunch of pixels. And these can in turn be represented as a matrix of numerical values. Now, the process of convolution involves multiplying the elements of that matrix sequentially with another, usually smaller matrix that is known as a kernel or filter matrix. And this results in deriving a newer, smaller matrix. And the interesting thing is this new matrix usually shows a specific pattern within the image. Now, let's say that we feed an image of a dog in front of a carpet to a CNN, and the kernel will be able to detect the borders between the dog and the carpet wall, and we know how hard that can be sometimes. And so it's able to detect this border. And in the next step, which is called pooling, a compressed version of this convoluted matrix that we just heard of is created. And this is known as a pooled matrix. So this convoluted matrix from earlier is multiplied with a filter matrix, and the results are then summed up as a maximum or average. And these values as the maximum or average value of the multiplications over a certain area of the matrix. And this leads to a size reduction of the matrices. And thus, you will slowly have many image features such as edges, curves, or shapes will result in more non-zero values when multiplied. This basically means that the compression effectively filters out any non-important elements, which is very useful. And these hidden layers each apply convolutions or pooling to the input data, with different nodes applying different pattern detection and complexity reduction filters. So basically, to summarize all of this, it sounded very complicated, but what it essentially does is it reduces complexity of especially hard input data, such as images and videos. And these specific neural networks can break it down to the essential core features of the images and then detect patterns within them. So that's what makes them very widely used as well as very applicable.
So amazing what you can do with math, and amazing how you can math to apply to images and to the pixels in those images, and to do exactly what Ani described. Another type of deep learning algorithm, or another family of deep learning algorithms, are recurrent neural networks, or RNN. And they are mimicking memory function, which allows them to analyze time series data, because they have insights on the patterns that occur over time in that data. This is useful for anywhere where you apply time series prediction, but also for anything where you have sequential data, which, for instance, is also given in speech or handwriting recognition, where the previous word that you've said before the word you're saying now, the context of what you're saying does matter in translation, for instance. Also, it's applied in anomaly detection, and it's applied in machine translation. Remember that the math executed at a node of a neural network is the multiplication of input and weight, the addition of a bias, and subsequently the input of the result is fed into a nonlinear activation function, such as a sigmoid function, for instance. Now, the memory function of an RNN, of a recurrent neural network, is achieved by exchanging the bias term, by leaving that one out, exchanging that with a multiplication, and the multiplication is of the result of a previous computation with a weight. So the result of a previous state that the network was in with a weight. The previous computation is the previous output of that node's activation function. So what came out of that node's activation function, but not this time, but one learning epoch before, sorry, one round before that. And the result of the node's activation function is multiplied with just another weight. So this is how the RNN introduces memory, how it is able to do so. And now we're going to look into one specific evolution, let's say, of an RNN.
Exactly. So this next one is a subclass, if you will, and it is a sort of upgrade to the RNN, and it's called a long short-term memory network. So a long short-term memory network, or LSTM, and they solve what is known as the vanishing gradient problem of RNNs, and they do this by introducing more math. Now, it's important to remember that the predictions of the network, remember, are just inputs into a loss function, and the output is then compared against the result, the expected result. Now, the gradient of this loss function serves to update the model weights for the next round of computation through backpropagation. In an RNN, however, the weight update might be very minimal or even zero because the gradient becomes smaller and smaller as it passes, so to speak, through the network to update the weights. So to avoid this, LSTMs introduce a so-called gates, and these are essentially just additional math operations on a combination of current as well as previous states, and they use activation functions. And what this means is that you can effectively allow the gradient to pass through the network during back propagation without vanishing to zero. So you don't have the problem of a gradient vanishing.
Let's look at generative adversarial networks, or GANs. And they are a bit spooky because they do not just learn representations in data, but they're also very useful to then create variations and actually fakes of that data. It uses an initial data distribution, and it consists of two neural networks. As you can guess, GANs are behind popularly known deepfakes, such as fake faces of news anchors or famous politicians. Usually this is done with GANs. GANs, however, are also useful to create simulations in science and games, such as simulating gravitational lensing in the research of dark matter, which could turn out to be very useful, as well as the creation of art and music. The intuition behind GANs, as mentioned, features two neural networks. One of them is a generator and the other is a discriminator. They sort of play a game with each other. The generator generates new content after learning the initial data distribution of the input content, and the discriminator compares that content with the input, with the original content. The generator's objective is to fool the discriminator, which is its adversary, so that's why it's called generative adversarial network. It fools its adversary into believing that the generator's output is part of the original data distribution, when in fact it is not. So in other terms, the generator has the goal to maximize the error rate of the discriminator until it is unable to distinguish the generator's output from the original data distribution. This concept of playing a game between simulating a game between a generator and an adversary has been applied earlier very similarly in the Turing test. An example of a GAN would be where you feed an algorithm a bunch of horse pictures, and it learns the distribution behind those horse pictures, and then it creates a zebra, and the adversarial cannot distinguish that zebra from any sort of real zebra. And once the loss function once the loss function is maximized, so the loss function of the adversarial is maximized because the adversarial doesn't know what's going on, then you have optimized the generator, and then you have optimized the GAN.
And now we move on to another family, which is in some senses similar, but in not exactly. So these are called autoencoders. And these are essentially deep neural networks that compress and decompress input to learn the representations and patterns within that input. So they compress or encode and then decompress it or decode the input. And depending on how they're set up, they can be used to reduce complexity of an input. Essentially, they're reducing dimensionality. and there are many use cases for reducing complexity, either for a subsequent learning algorithm, for anomaly detection, image processing, drug discovery, machine translation, or even to generate new variations of the input. And that specific case is called a variational autoencoder. We'll get to that in a bit. So an autoencoder uses adjusting weights and activation functions, such as latent variables or even latent space, at hidden layers to encode and decode the input, so that its output is identical to the input. And in this process, it learns a lot about the input data, it learns about many useful features. Now, we mentioned the variational autoencoder, or VAE, and the VAE essentially has additional regularization techniques. Remember, regularization is the process where you try to reduce mathematical complexity by penalizing the algorithm for it. And these additional regularization techniques are introduced to prevent the algorithm from overfitting. That means to make it more applicable beyond the training set. In a denoising autoencoder, you basically feed additional noise to prevent the autoencoder from simply copy pasting the input data to the output. And in a VA, another interesting thing to note is that the latent space consists of distributions instead of single points. And what this means is that you can now decode process, or it allows the decoding process to vary over those distributions, meaning that you can now create new variations of the initial input. So as we saw, there are many use cases for this, but we'll get into more specific ones later.
So those are really the most well-known and used deep learning algorithms, but we don't want to spare you also the ones that are less well-known or have been used earlier and are not as popular right now. One of them is the deep Boltzmann machines. And all of these deep learning algorithms, if you look at them, all of them that we've looked so far, they are linear in a sense that you feed the data through the network and then you propagate it back to compute some kind of error. Deep Boltzmann machines, however, are undirected graph networks, which means data can flow between nodes in both directions. So there's not a particular node which is before or after a particular node, but it goes in both directions. Now, Boltzmann machines, why is it a deep Boltzmann machine? So it's a Boltzmann machine, an undirected graph network that has several hidden layers to it. Now, the exception is a restricted Boltzmann machine. So that's something different. The nodes here are grouped into hidden layers, and connections between them are restricted to interlayer-wise connections. So some nodes can make connections with other nodes, but not all of them. Boltzmann machines and also deep belief networks, which also is one that is not as popular anymore, but was quite popular just a few years ago, are not as en vogue at the moment. But they might see a renaissance in the future and might become very important and see new applications found out by researchers applied to them. Just like many other concepts that we described here before. There are also several other algorithms which we haven't covered that face the same momentary fate, like self-organizing maps, which are useful for clustering. Deep belief networks, as mentioned, they are good for generative models, and so-called radial basis function networks, which are named after the type of functions that they use for activation, which are radial basis functions.
So now we've covered the most important types of deep learning algorithms, but let's take a look into not the many applications, because it's still a very young, a very nascent industry. So we can expect a lot of progress in the next few years, but there are some areas where deep learning has already been applied to extensively, and we'll just cover these most mature applications. Simply because the list of potential applications of deep learning are just limitless. We'd have to go on a 24/7 stream for a few months to cover all of them. Maybe someday. But to just give you a short overview over the industry, the global deep learning industry is estimated to currently account for about $4.4 billion, which is pretty big in and of itself. But by 2027, get this, it is expected to grow tenfold to $44 billion, tenfold, with a Bitcoin level growth of 37 kger over the growth period. So machine learning and deep learning really are growth freaks.
Now, somewhat unsurprisingly, in this very much growing market, the main competitors in the market are big tech companies. And the reason is that you need to have both large amounts of consumer data or large amounts of data in general, and also great talent to research and work on those deep learning algorithms. So the world's largest tech software and hardware companies are good candidates. And in fact, you see that with Google DeepMind, Facebook AI Research, Microsoft Research, Amazon Web Services and their research department, IBM, Intel, Fujitsu, Nvidia, Samsung, Qualcomm, Huawei, and Twitter Cortex as being the main competitors in the space driving the field forward because they can rely on the data and the talent.
Now, one of the biggest applications next to speech recognition, is speech recognition and natural language processing. And these are the most widely adopted use cases of deep learning currently. And they both rely on deep learning algorithms which possess memory function, because as we know, it's important to not just understand words individually, but also in the context of sequentially appearing together in a sentence or paragraph. So this means that if you remember, the appropriate algorithm types are RNNs or LSTMs. Google Translate uses LSTMs to perform machine translation. But interestingly, Google's Word2Vec, another algorithm that they own, uses a different concept. And the way it works, they model words in high dimensional vector spaces and then learn the context of them through the semantic distance, that is, the distance in the vector space between them. And this is known as word embeddings. And a simple example would be the semantic distance between king and queen, or queen and princess. And this indirectly gives us the distance between king and princess, and so on. And these word embeddings serve as an input to an RNN. And on the other hand, on speech recognition, the additional challenges is the input type of the data, which is audio. Then you have the variation of it. So if someone coughs, mumbles, speaks in a strong accent, as well as the high tempo of sequences being produced. LSTMs also perform best here because of their ability to work with sequential data. And as we mentioned before, the gates that are installed prevent any vanishing gradients. And most major commercial speech recognition systems, such as Amazon's Alexa, Apple's Siri, Microsoft's Cortana, Google Now, or Baidu's voice search, use some form of deep learning.
However, probably the most well-known application of deep learning, I guess many people, when they hear deep learning, they think about image and video recognition first, and generally computer vision. Now, this includes object recognition, object identification or detection under certain conditions, as well as motion tracking and analysis, restoring and reconstructing images in scenes, and more tasks related to vision and images and videos. The standard for computer vision and deep learning are those convolutional neural networks that we talked about. Let's look at three interesting examples. The first one is medical image analysis, where you can detect diseases to diagnose a patient, for instance, by detecting conditions that determine or define cancer or tumors. The second example is autonomous vehicles, as well as robots in general, and futuristically also unmanned aerial vehicles. For this one, stay tuned on our Future of Mobility episode. They are also using, or they are primed to use, computer vision to navigate in space and identify objects. A last example that is interesting is LipNet, which is a lip reading software that achieves over 95% accuracy, which lip reading also is a an image, a computer vision task, because the computer needs to recognize what's going on with the lips of that person.
Now, deep learning can also be applied to speech or media creation and output, such as video, music, or even art. Um, the best suited for these tasks are generative models because the algorithms have to generate something. So we're looking at GANs or variational autoencoders. For example, Google DeepMind's WaveNet is a deep neural network that gathers audio and lets machines talk. So the algorithm is actually able to produce sound output which resembles that of a human voice. It is also able to model any kind of audio, including music. So it's very interesting to think that an algorithm can produce human sounds and communicate like a human.
Coming back to medicine, a lot has been researched recently on applying deep learning to drug discovery and synthesis.
Yeah, so I'll kick off with the examples. For instance, deep learning can predict the properties of certain of drugs. For instance, its toxicity, which is very important, and it does this by encoding its molecular structure as a vector or a text or graph, and then feeding this information through a deep neural network. And it goes without saying that you need a lot of examples, including their toxicity values, to accurately predict new examples. But it's nonetheless very exciting.
Before we go into the next example, we have to quickly talk about proteins. So proteins serve a lot of important functions inside our bodies. And Google DeepMind managed to solve a 50-year-old problem related to proteins, which is accurately predicting the resulting protein structure from the folding process of a bunch of amino acids, which in itself is a very exciting deep learning application to medicine. The structure of a protein largely determines its function. So this is why this is exciting. The program called AlphaFold makes predictions of the distances between amino acids before they fold.
And deep learning can also be applied to predicting whether a particular drug can bind to a particular protein. So, for instance, a protein outside the cell membrane of a virus, or an example would be to measure whether a protein would bind with a virus in order to shut it down. And this is useful for drug design as well as discovery. Data representations of both medical compounds and proteins are needed, as well as labels regarding whether they bind or not. And depending on the input format, there are a wide variety of deep learning algorithms that are suitable. A deep neural network for vectors would be RNN or LSTM, and for text, and a CNN for images.
Drug discovery is a tough problem. You need to design new drugs which display exactly the desirable properties that you want to have. Generative models like GANs and variational autoencoders have been applied to this problem in research. The search space of potential molecules is very large, especially if you combine them, which makes this a hard problem to solve. However, the company Atomwise has built their AtomNet platform, which trains on 3D image representations of chemical interactions using CNNs. It identifies patterns in those chemical reactions, such as aromaticity or hydrogen bonding, to predict novel candidate biomolecules against disease targets. It has already been used to predict such biomolecules that could target Ebola or multiple sclerosis and explore questions related to cancer, neurological diseases, or antibiotics.
And now taking a big leap from medicine, deep learning can even help in financial fraud detection. And this can be achieved by recognizing anomalies in time series data. For instance, by finding a combination of feature characteristics of a certain of financial transactions that can identify it as a fraud. So deep learning has shown to be quite successful doing so. And this happens by feeding a deep learning algorithm with a lot of examples of transactions that are either labeled as fraud or not. And if you remember from our last episode on machine learning, this is a classic supervised learning problem.
Now, Deep learning can also be applied to recommender systems, and today's recommender systems are sort of rudimentary. They usually rely on similarities between two users in terms of their consumption patterns, or rudimentary similarities between two objects that you show to the user. So, for instance, similar movie titles or similar genres of those movies. Deep learning has the ability to go much deeper in terms of analysis of the content. For instance, by learning different rhythmic or energetic patterns in music and using them to recommend music to users which is structurally similar to the one they liked before, with a higher chance that they will also like the new music. Another approach would be to base recommender systems on the similarity not of the user's consumption, but the similarity of their personalities, which is going beyond socio-demographic traits and more into character traits. For instance, you could use a personality assessment to determine those. Early versions of personality-based recommender systems working with rudimentary character and preference tests are already in use in dating apps. When it comes to search and text, Google's search engine has already incorporated deep learning. We have to remember that recommender systems are somewhat limited by design and on purpose, as they do not necessarily focus on optimizing value for the individual user, but rather to optimize the revenue for the operator. Sometimes these two are conflicting targets. For instance, when you think about favoring a higher paying user over others in dating apps. So you could show a non paying user and it could be a better fit, but you still show the higher paying user probabilistically because that generates you revenue. Or another example would be attention generating content over well researched content in content platforms. So content platforms want to generate clicks, so they do not necessarily show the best fitting result to the users or the most valuable result, but the one that gets clicked most, which might not necessarily be the one that the user actually wants to show, wants to consume, but just based on its characteristics, it's being generally clicked a lot.
So these are the most mature applications of deep learning, and we're sure that even by the time that we upload this episode, there will be new applications, and this industry is developing very fast, as we have seen. But let's get to some of the major challenges of deep learning. And one of the biggest and obvious ones that we mentioned at the beginning is that in most cases, for deep learning, you need large data sets with millions of examples in order to train a DL algorithm to be useful at all and to learn these representations and patterns um, so that it can generalize and create findings and predictions for new unrelated examples. And even though access to machine learning tools in education, data storage, and even processing power are widely available due to the internet and the cloud, large data sets remain mostly proprietary with very few examples. So, the bottleneck to fast progress in DL is the availability of vast amounts of data to researchers and entrepreneurs, but providing this data on a public scale is another data privacy issue onto itself.
Deep learning relies on mathematics, and mathematics are a beautiful language. In fact, many would argue it's the most beautiful language in the world. And it has many advantages, but it has one major disadvantage, which is also one of its most useful advantages, which is it compresses meaning. And for deep learning, that is both great, but also potentially something that makes it hard to explain what it actually does. Many deep learning methods often represent a black box because the mathematical function or the accumulation of features makes it then hard to distinguish which features have how much weight into what's going on in the algorithm. So it might be hard to or impossible to visualize or even understand how they solve a particular problem or further digest their results. This makes sense as part of the reason we use them is to solve complex problems, right? With large and complex mathematical representations needed and processes based on huge data sets which we couldn't do by ourselves. So that's why we invented them in the first place. This is also a challenge when it comes to building intelligent machines in the future, because those should understand and reason causal relationships and perform logical inferences beyond of what they've learned in their particular application.
And as we attempt to automate more and higher responsibility tasks to deep learning, We rely on them to not just be somewhat accurate or very accurate, but very, very accurate. So we're talking above 95%, in some cases, hopefully even 100%. Um, think about security critical face detection systems that rely on CNNs for face detection. Many state of the art DL algorithms still fail to perform at such a high accuracy, and this can have very expensive costs. So there's still a long way for us to go to be able to reach that 100% accuracy so that we can safely entrust certain vital tasks to DL algorithms.
Expensive cost and vast consequences or detrimental consequences are also potentially caused by security threats. And deep learning algorithms do remain vulnerable to adversarial or malware attacks, where attackers would manipulate the inputs to the algorithm in a way as to achieve a malicious output. This was demonstrated, for instance, for Google Now's voice command system, where a group was able to create certain sounds, and those sounds, fed as an input into the system, led the system to open a malicious web address and download malware.
That is scary. Um, Another concern regarding such automated decisions is ethics. So we rely on deep learning algorithms to take critical decisions in all of our societies somewhere, probably from how an autonomous vehicle should behave in an ambiguous threatening situation, or what standards a credit rating algorithm should apply. And we should, as societies, come to an agreement on what these standards should look like and how they should be enforced. This shouldn't just be outsourced to private companies and software developers. So very much the way we build our constitutions democratically, the ethical standards for deep learning algorithms must also be reached democratically.
Now, for many of the technologies that we present here in this podcast, and many that are being conceptualized and thought through, the emergence of artificial general intelligence is a preset for those to thrive and for those to really fulfill their potential and to really solve their problem. However, the concerns questioning whether AGI and superiority of machine intelligence, also called technological singularity, if we reach that point when AI is smarter than humans, if we reach that singularity, the debate goes on whether this will happen, whether it will ever happen, and whether also it should happen. If it happens, AGI will be benign to humans or not. That's another question. Whether it can be conceptualized to display or develop ethical standards in situations that Ani has mentioned, but also in situations that go much further. Also, if they can display critical reasoning, something like consciousness or sentiment, as well as recognize bespoke from humans and interacting with them successfully. Some, including at least publicly the currently richest man of the world, even go as far as to identify increasingly close human AI integration to cyborgs, also called transhumanism, as the most feasible or even only option to sustainably address these concerns, which is also what we discussed in our brain-computer interface episode, which I believe is episode number 6. So finally, if AGI progression will happen, the question regarding the rights of AGI or machine systems in general might also become critical to ask, not just their duties, but also their rights. Given that they might become conscious beings, sounds a bit spooky, but it might happen, and or feeling subjects. To learn more about transhumanist utopian technology, check out our episode on brain-computer interfaces. I promise you will not regret it, and it's definitely an exciting one.
Speaking of exciting, we get to our most exciting part, our favorite part, the utopian day in the life, this time enabled by deep learning. And well, I wake up in the morning. My smartphone, smart glasses, and all wearables are fully integrated with speech recognition and my personalized AI assistant. And I basically don't even use my fingers or anything to interact with the devices. If anything, at most, I sometimes feel like I want to take extra steps, and so I use voice commands. But usually, my BCI does everything for me. And the deep learning algorithm that is powering my AI butler, let's call this butler Jarvis. is already taken care of my schedule today. It has also understood how I feel on certain days, given the weather and um, other factors, and it has accordingly prepared dresses, a lunches, moved certain meetings around to just create a smooth and seamless day of smooth and seamless utopian day.
So because all of this is automated and because also almost all necessary work is automated, I have a little bit of an extended morning coffee here. What we can also do now, as opposed to earlier, where we could just outsource rudimentary tasks or basic cognitive tasks, we can also outsource creative work if we want to. We can use GANs, RNNs, and variational autoencoders to do so. So I have some extra time to spend in the morning. In my case, I can tell you a little bit about my startup. I decided to found an organization that advocates and performs education about rapidly evolving technology available for the general public.
Is it
I
called UTX?
Yeah, I mean, why not? Maybe maybe honoring a previous or still existing, obviously, podcast that was going into that direction as well. So I'm really going into a scene which is already quite advanced, thanks to something like UTX. It's a society that already has a quite intelligent education system fitting our needs, educating us about AI and how to work with it, how to collaborate with it. So yeah, I hop in an autonomous vehicle to be taken to the office.
And well, as I'm in my in actually it's an autonomous vehicle that I share with my friends that earns me some money during the day. I digitize some documents with my phone, and that happens flawlessly within minutes. It uses a advanced CNN and a combination of CNN and RNN to detect both pictures as well as documents and handwriting. And this data is then available to directly do computations on top of an automatically generated Excel file or database instance or update.
At lunchtime, I'm reading the news, and sadly, I'm reading about a major virus outbreak, which is now contained. It was contained after just 2 days after it emerged. Uh, Once a new germ, virus, or bacteria or disease pops up, we have a drug or vaccine against it available within several hours. Most of which is spent on coordination and approval, because an algorithm utilizing existing data, pre-trained algorithms, and generative models is finding a solution just shortly after we have taken the germ to the laboratory for analysis.
And of course, there is no need for any expensive vaccination campaigns because the information to produce these vaccines, this mRNA vaccine specifically, has been sent via the internet to my 3D printer at home, and my BCI slipped it into the coffee in my evening coffee, and I didn't even notice that I took it, and I didn't even know that I gained immunity to this new germ that has now been out for 2 days, which is a big deal, which some consider already very slow. And so in the afternoon, I'm at work, and I use a combination of a LSTM and a VAE, and it allows me to set up some videos, PowerPoint presentations, graphics, and even music just with voice commands based on feeding the algorithm previous work of mine or even open source work. And it even combines information on how the client, on which type of graphics, PowerPoints, videos, and music the client likes to optimize it. Um, and it then creates a variation while still applying the correct styling and formatting.
So I have to admit to you that I'm not very interested in architecture. I'm curious about a lot of things, but architecture has really not touched my soul and heart and mind as much. But now a colleague of mine has sent me an article about a completely deep learning based built and designed house. And I sort of spent some time on that article. Now, via a variational autoencoder based algorithm is showing me similar articles to those in order to keep me happy, because it's also showing me stuff that I'm not previously consuming as much. and thus pulls me out of my filter bubble. I am happily thinking about the fact that I am fully owning my personal data, because data is everything in this kind of economy, and I get paid for it whenever a business uses it. They cannot even use that without me getting notified and automatically being paid. On the other hand, I'm paying for those algorithms that are distributing me these new type of content. So what really is generated is a symbiosis between users and businesses, where users get paid for their data, and thus they are incentivized to really give their data to the businesses, and the businesses are incentivized to build algorithms that feed value instead of just optimizing attention, and to optimize these algorithms based on a lot of more available data, because users are not reluctant anymore to send that data over. The reason for that is also a concept that we will discuss in the third episode of the machine intelligence series in our podcast, which is going to be episode number 13, about edge computing, about federated learning, and about the third one I actually don't about biological computing. So those will be the three concepts that we're going to look at in our third episode of the machine intelligence series.
And after that, we will, of course, continue to the other many utopian technologies that are there waiting to be explored, explained, and dreamt about how they can bring about a more utopian day in the life for us. And as always, you can find us on YouTube, on Spotify. Or you're probably watching this on YouTube, but you can also find us on Spotify. We even exist as a blog on Medium. Head over to utechniax.medium.com. And we'd also like to let you know that we know that the UTX podcast clips are quite long, and maybe you're just looking for one specific segment that you enjoy the most. We've transformed the episodes into bite-sized little clips that we upload on a daily basis. So stay tuned for our 4 p.m. Central European time UTX clips. And as always, stay utopian.
Your Techniax.